Hey everybody, welcome back to Intermediate Algebra, and today we're in section 6.7 where we're going to be talking about how to solve quadratic equations using the zero factor property. So all through chapter 6 we've been learning how to factor polynomials, and now we're going to use that factoring to solve a new kind of equation called quadratic equations. So our objectives in this section will be to solve quadratic equations using the zero factor property and also solve some other equations using the zero factor property. Let's get started. So I said a while ago that we can use our factoring skills to solve some types of quadratic equations. So you might be wondering, what exactly is a quadratic equation? Well, a quadratic equation is just one that has an x squared term. So it is an equation that can be written in this form where we have an x squared term and possibly an x term and possibly a constant, and all of those can be written on the left side of the equal mark and set equal to 0. And the form that we have here is called the standard form. So let's go ahead and get some examples of quadratic equations. X squared plus 5x plus 6 equals 0 is an example of a quadratic equation. Now notice that in order to be an equation, it needs an equal mark, of course. You couldn't just have x squared plus 5x plus 6 and call that a quadratic equation, because without the equals 0, we don't have an equation. Every equation has an equal mark. Here's another example of a quadratic equation. 2x squared minus 5x equals 3. Now this one has the constant on the right side of the equal mark, but it's still quadratic because it has this x squared term. And notice that if we wanted to write this in standard form by moving the 3 to the left side of the equal mark, we could do that, and then it would look just like this. How about x squared equals 4? Well, of course, if we move the 4 to the left side of the equal mark, we would have x squared minus 4 equals 0, and that would be standard form for the quadratic equation because we would have an x squared term, and b would be 0 because we don't have an x term. That's okay. And then the c would be negative 4. So this is a quadratic equation. Now, one way to solve quadratic equations is by factoring and then using the zero factor property. The zero factor property is a really simple idea that you already know. You just may not have ever given a name to it before. So here's what the zero factor property says. If a and b are real numbers, in other words, any two numbers that we're used to dealing with, and you know that a times b equals 0, then you know for sure that either a equals 0 or b equals 0. Let me say that again. If you know that a times b equals 0, then you know for sure that either a equals 0 or b equals 0. Now notice that 0 is the only number that has this property. If you have a times b equals 1, then you still don't know anything about a or b. If you know that a times b equals 5, you still don't have any information about a or b. But if you know that a times b equals 0, then for sure one of the numbers has to be 0. That's why it's important that we only use factoring when we've got one side of the equation equal to 0. For our first example, we have an expression that's already in factored form equal to 0. So this one did not start out in standard form. They gave it to us already factored. Now the zero factor property says that if this times this equals 0, then one of the factors will have to be equal to 0. So the x value that causes this factor to equal 0 is a solution of this equation, and the x value that causes this factor to equal 0 is a solution of the equation. So in order to find the two solutions, we will take each factor and write equals 0 after it, and then find those x values. If x plus 3 equals 0 and we subtract 3 from both sides, then we find out x equals negative 3. And if 2x minus 1 equals 0, then we add 1 to both sides. That gives us 2x equals 1. And to isolate the x, we divide both sides by 2. And now we see that x equals 1/2. So x equals negative 3 makes this equation true. because it makes this factor equal 0, and x equals 1/2 makes this equation true because it makes this factor equal 0. So both of these numbers are part of our solution set. So we would say that the solution to this equation is -3, 1/2. Now, notice that the order does not matter here. The curly braces are a container for a list of numbers, and the order that the numbers are listed in is not important, as long as all the numbers are in there. Now, we can check both of these solutions, so we'll go ahead and do that. We won't do it on every problem, but we'll do it here. If we plug in -3 into our original equation, you can see that -3 plus 3 is 0, and you could figure out what this other factor is. It would be -6 minus 1, it would be -7, but that's not really important because 0 times anything would be 0, and that would make the equation true. And now let's check the 1/2. So if we plug 1/2 into the equation, the 1/2 plus 3 is 3.5, or 7/2, and then 2 times 1/2 is 1, and so we have 1 minus 1, which is 0, and 7/2 times 0 is 0, and so that value made the equation true. So you can see that both numbers are solutions of that equation. Here's part B of example 1, and again we're using the zero factor property. This expression is already factored for us. So we know that if this times this is equal to 0, one of these factors has to be 0. Either y equals 0 or 3y minus 4 equals 0. If y equals 0, there's nothing to solve. That's just 0 is one of our solutions. But if 3y minus 4 equals 0, then we add 4 to both sides. We have 3y equals 4 and divide both sides by 3. And we find out y would be 4/3. So the solution set is 0 and 4/3. Now let's check both of these. If you plug 0 into the original equation, then you have 0 times this quantity in parentheses. 3 times 0 would be 0, and 0 minus 4 would be -4. So we have something that says 0 times -4, and that is equal to 0, and that matches the right side, so that's a good solution. And if we plug in 4/3, we have 4/3 times 3 times 4/3 minus 4. Well, when you do 3 times 4/3, the 3's are going to cancel, leaving you 4/3 times 4 minus 4. And 4 minus 4 is 0, so 4/3 times 0 is 0, and that means that number is a good solution. And so we verified both solutions here. Now let's look at example 2 together. We're still solving quadratic equations, but in example 2, the equation is not given to us in a factored form. So notice that we have x squared minus 5x equals -6. Now remember, if we're going to use factoring in the zero factor property, then we need to have a 0 on the right side. Because if you factor this left side, you could factor out x as a GCF, but the factoring wouldn't do you any good because your factoring would be equal to -6. Factoring is only helpful if you have it equal to 0. So what we'll have to do first is add 6 to both sides, and that will give us the equation in this form. X squared minus 5x plus 6 equals 0. So this is a trinomial, and we know that it will factor into two binomials if it factors at all. So we are reversing the FOIL process here. First times first has got to be x squared, so that's going to be x times x. The last times last made a positive term, so these two signs have to be the same, and in order to get a negative middle term, they're both going to have to be minus. Now, your last times last has to make 6, so it could either be 2 times 3 or 6 times 1. Since the signs are the same and you need the middle term to add up to -5, let's go with 3 and 2. So now, as a check, I won't write it out, but just as a check, you can see that first times first makes x squared, outer and inner make -2x minus 3x, so that adds up to the proper middle term. And then -3 times -2 makes +6, which is the right last term here. So this is the right factoring. Now that we have our factoring and we know it's equal to 0, now we can write either x minus 3 equals 0 or x minus 2 equals 0. If x minus 3 equals 0, we add 3 to both sides, x equals 3. If x minus 2 equals 0, then of course x equals 2. And so those are our two solutions. And let's just check this one real fast. We'll stop checking real soon, but for right now, let's go ahead and check a few more. We're plugging 3 in, so we're going to check the 3 first. So if we plug in the 3, we'll have 3 squared minus 5 times 3, and that's supposed to equal negative 6. Well, on the left side, 3 squared would be 9, and 5 times 3 would be 15, and 9 minus 15 is negative 6, and that's a match for the right side. So 3 is a good solution, and let's try 2. Plugging in the 2, we get 2 squared minus 5 times 2. Well, 2 squared is 4, and 5 times 2 is 10, so 4 minus 10 is negative 6, and that's also a match. And so our final solution set is 3 and 2. And remember that we said it does not matter which order you list the solutions in. Here's part B of the same example. So we have y squared equals y plus 20. Now remember, in order to do any factoring, you need one side of the equation to be equal to 0. So let's take these two terms and move them over to the left side. So that's going to give us y squared minus y minus 20 equals 0. And now you can see that we have a trinomial, and that's going to factor into two binomials. So first times first is y squared, so that could only be y times y. The last term is negative, so that means the signs here need to be different. And last times last made 20. So our choices for 20 are either 1 times 20, 2 times 10, or 4 times 5. If you know that the middle has to add up to negative 1y, you know that you're going to want a negative 5 and a positive 4 in order to get that right middle term. Okay, now if this times this equals 0, either y minus 5 equals 0 or y plus 4 equals 0. If y minus 5 equals 0, then y is 5. And if y plus 4 equals 0, then y is negative 4. So those would be our two solutions. Let's check each of them. If we plug in the 5, then we have 5 squared equals 5 plus 20, just plugging the 5 in place of y. So 5 squared is 25, and 5 plus 20 is also 25, so we have a match. That means 5 is a good solution. And when we check negative 4, we have negative 4 squared equals negative 4 plus 20. Well, negative 4 squared would be positive 16, and on the right side, negative 4 plus 20 is also positive 16, so that's also a good match. And so our solution set is 5 and negative 4. So let's kind of summarize what you just saw in the last example. When you want to solve a quadratic equation using the zero factor property, the first thing is to write the equation in standard form, and that means all terms on one side of the equal mark, and it's best to put the powers in descending order. In other words, the x squared term comes first, then the x term, and then the constant, and then you should have equals 0 on the other side. Get it in this form first before you start trying to factor. Then factor completely. If there's a GCF, factor that out first. Then after you factor out the GCF, if there's a remaining trinomial, then factor that trinomial. When you've got it completely factored, then you can apply the zero factor property. Set each factor that contains a variable equal to 0. Factors that do not contain a variable have no effect on the solution anyway. Then you'll solve the resulting equations and check if you have time, especially if you have a calculator. Go ahead and check your solutions because it doesn't hurt, and then write your solutions in curly braces, and the order that you write the solutions in is not important. Okay, another example. Here we have 4p squared plus 40 equals 26p. So clearly this is quadratic because we have the p squared term. And clearly we need to move this 26p over to the left side because we need one side to be equal to 0. So I'll say minus 26p on both sides, and that's going to make us have a negative 26p here. And let's write it in the middle so that we have the p squared term and then the p term and then the constant. So we'll have 4p squared minus 26p plus 40 equals 0. Now, I know you're probably looking at this coefficient here and going, oh, when the coefficient gets big, it makes the factoring a lot harder. And that's true. Well, it makes it a little trickier. You have to be more careful because it creates more options, more different combinations that we have to try. But also notice here that 2 goes into all of these numbers. So why would I do factoring with large numbers like this when I could factor out a 2 and work with smaller numbers? So let's factor out a GCF of 2. 2 times 2p squared would make that first term. And 2 times minus 13p would make that middle term. And 2 times positive 20 would make that third term. And notice that we have it here equal to 0 because it's important when you're factoring that every line be shown as equal to 0. If your factoring is not equal to 0, you can't take the next step and solve. So you've always got to have an equation on every line, and the right side must be equal to 0. Now let's see what we can do about this trinomial. Remember, we're just reversing the FOIL process. So don't lose your GCF that you pulled out, but do take that trinomial and break it into 2 binomials. Now first times first has to be 2p squared. So that's going to be 2p times 1p. Last times last made a positive number, so that tells us these signs have to be the same. And if they're the same, they both have to be the same as our middle term, so they both have to be minus. And then last times last made 20. So your choices for 20, again, are 1 times 20, 2 times 10, or 4 times 5. So you can probably tell that 1 times 20 is not right because I couldn't put 20 here. And if I put 20 out here, it's going to make the outer times outer way too big to get that middle term. 2 times 10 won't work because if I put a 2 here, I'll have another GCF, and that's not right. And if I put the 10 here, that parentheses will have a GCF. But we know that our parentheses can't have a GCF because we already pulled out the GCF. So I'm left with 4 times 5. So the 5 is going to have to go here, and the 4 here. And let's see if that works. If this is the right factoring, then outer plus inner will add up to that middle term. Do not say to yourself that 4 times 5 is going to have to make 13. That's not the way it works. Outer plus inner has to make negative 13p. So let's see. 2p times negative 4 is negative 8p. Negative 5 times p is negative 5p. Negative 8p and negative 5p together make negative 13p. And so this factoring is correct. And so now, if this times this times this equals 0, then one of our factors has to equal 0. It can't be this one because this one does not contain a variable. So you really don't even have to mess with this one. But it could be this one. So let's take 2p minus 5 and set that equal to 0. And we'll also get a solution from this factor. So p minus 4 could equal 0. For the first factor, if 2p minus 5 equals 0, then add 5 to both sides and 2p equals 5, and divide both sides by 2, and we find out that p is 5 over 2. So that's one solution. For the second factor, if p minus 4 equals 0, then you add 4 to both sides and p equals 4. And so our solution set here is 5 over 2, comma 4. And again, the order doesn't matter. And again, if you have a minute, you should take a calculator and just plug in each solution and make sure that both sides of the equation match for each solution. But we're not going to do that here. I'm just going to trust you to do that when it's necessary for you to check your work. And let's move on to example 4. So here we have 16m squared minus 25 equals 0. So notice that this is a difference of squares. These are really easy to factor. You remember? So to factor this, we'll say that's going to make 2 binomials. One is going to be a sum and the other is a difference. 16m squared is the square of 4m. So we're going to have 4m in each parentheses, and then we need a minus and a plus, and the 25 has got to be 5 times 5. So if you use the FOIL method to multiply this back together, you'll see that you get 16m squared minus 25. So this factoring is good. If this times this equals 0, then one of the factors has to be 0. So we'll take each factor and set it equal to 0 and find out what those m values are that are causing those factors to equal 0. So if 4m minus 5 equals 0, then you add 5 to both sides. 4m equals 5, and divide both sides by 4, and m equals 5/4. For the other factor, you subtract 5 from both sides, and you get 4m equals negative 5. Divide both sides by 4, and you get negative 5/4. So this is the way it works when you're solving a difference of squares. The numbers in each solution will be the same, but they'll have different signs. So just like we see here, positive 5/4 and negative 5/4, that's typical for difference of squares. So that's our solution set here. For part B, we have y squared equals 2y. Now this is quadratic because it has a squared term and nothing higher than that, but it's not in standard form, so I can't solve it yet. I have to move the 2y to the left side. And notice when we do that, of course we get negative 2y, but notice that we don't have a trinomial. And also, it's not a difference of squares like this binomial was. So this expression is not going to factor into two binomials, but it does have a GCF. Both terms contain a factor of y. So we will undistribute the y. We will factor out the y as a GCF. Y times y would make y squared, and y times negative 2 would make that second term. Okay, now if this times this equals 0, one of these factors has to be 0. If y equals 0, then that's fine. And if y minus 2 equals 0, then you add 2 to both sides and y equals 2. So these are our two solutions here. The solution set is 0 and 2. Now in part C, we have something a little different. This left side is in factored form, but the right side is not equal to 0. So you cannot say k equals 3 and 2k plus 5 equals 3. 3 doesn't work like 0 does. We have the 0 factor property. We don't have the 3 factor property. These factors need to be equal to 0. So what we're going to have to do is get the 3 back over here on the left in order to have a 0 on the right. But then your factoring won't be any good. So what we're going to have to do is distribute that k and then refactor after we get the right side equal to 0. So distributing the k, we're going to have 2k squared plus 5k equals 3. Now subtract 3 from both sides. And you'll have 2k squared plus 5k minus 3 equals 0. This is a trinomial. And when we factor it, it's going to make two binomials. And that factoring is going to be equal to 0. And that's what's going to let us move forward and find the solutions. So we'll be reversing the FOIL process on this trinomial. So we know that when we factor a trinomial, it breaks down into two binomials. First times first has got to make 2k squared. So that's going to have to be 2k times 1k. The last times last made a negative number. So that means our signs here have to be different. Which one should be plus and which should be minus? Well, we don't know yet. So we'll just have to put the signs down whatever way we think is best. And then last times last had to make 3. So basically our only choice of factors is 1 times 3. Let's put the 1 here and the 3 here. Now let's see if we guessed right. Outer plus inner should add up to positive 5k. Okay, outer times outer is 6k. Inner times inner is negative 1k. 6k minus 1k is positive 5k, and that's what we needed for the middle term. So that tells us this factoring is correct. Now, if this times this equals 0, one of these factors has to be 0. So we'll have 2k minus 1 equals 0, and k plus 3 equals 0. If 2k minus 1 equals 0, then add 1 to both sides, and you have 2k equals 1, divide both sides by 2, and you have k equals 1/2. And if k plus 3 equals 0, then subtract 3 from both sides, and you have k equals negative 3. So our two solutions here are 1/2 and negative 3. Now in part D, we have a similar situation. So if you wanted to pause the video and try this one on your own, I think that would be a great idea. And now let's go through it together. So we do have factoring here, but the factoring is not equal to 0. So basically we have to redistribute that p and move the 2 over to the left side so we can have the 0 and do factoring from there. So we'll distribute the p. That gives us 4p squared plus 7p. And on the right side we have 2. So now let's subtract 2 from both sides so that we can have a 0 on the right side. And now we'll have to factor this trinomial into 2 binomials. Notice that these 3 terms do not have a GCF, so we can't factor anything out. We'll just have to go with what we have here. But that trinomial is going to factor into 2 binomials. So we have 4p squared. That could either break down into 4p times 1p or 2p times 2p. Let's start with 4p times 1p and see where we go from there. All right, last times last made a negative, so that tells us that these signs need to be different. And our last term is 2, so basically our only choice of factors is 1 times 2. Now the 2 can't go here, because if I put the 2 here, I would create a GCF in that parentheses. And this factoring is not supposed to have a GCF. So I need the 1 here and the 2 here. All right, now let's see if outer plus inner adds up to positive 7p, and it does. Outer times outer is 8p. Inner times inner is negative 1p. 8p minus 1p is positive 7p, so this factoring is good, and we can go ahead with our solving process. So if this times this is 0, then one of the factors has to equal 0. So either 4p minus 1 has to be 0, or p plus 2 has to be 0. If 4p minus 1 equals 0, that means 4p equals 1, and dividing both sides by 4, that means p equals 1/4. On the other factor, if p plus 2 equals 0, then p equals negative 2. So for this equation, our two solutions are 1/4 and negative 2. And again, just a reminder that you can only use the 0 factor property if the right side of your equation is 0. So that's why it was necessary for us to do all this work here, even though we started with a factored form. Don't be one of those people that just takes your factoring and sets it equal to the right side. That is not how it works. The right side has to be 0 in order for you to use this property. Now let's take a look at example 5. So this one says z squared minus 22z plus 121 equals 0. So it is a trinomial and it does not have a GCF, so we'll just go ahead and try to break this down into 2 binomials. Z squared has got to be z times z. The last term is positive, so that tells us that these two signs have to be the same, and they both have to match the middle term, which means they both have to be minus. And of course 121 is 11 times 11, and that looks good because that's going to give us the middle term that we want. But now notice that both factors are the same. Well, there's no use in solving both of them because they're both going to give you the same answer. They're exactly the same. So we'll just solve one of them. If z minus 11 equals 0, then z equals 11. And for the other factor, z also would equal 11. So we have two solutions, but they're both the same. So when you write it down, you only need to write it one time. When both solutions are the same, do not write the solution twice. You only write it once. Let's try that again over here. On part B, we have 9y squared plus 30y equals negative 25. Of course, before you start trying to do any factoring, you need the 0 on the right side. So we'll add 25 to both sides. And that will give us a right side of 0. And now, when we factor, of course, this is a trinomial and it does not have a GCF, so it's going to break down into 2 binomials. 9y squared, the most obvious thing to try is 3y times 3y. And then for 25, the most obvious thing to try is 5 times 5. Now the signs are going to have to be the same and they're both going to have to be positive. And of course we're going to try 5 times 5. Let's see if this arrangement gives us a middle term of 30y. Well, outer times outer is 15y, and inner times inner is 15y. So yes, 15y plus 15y is 30y, and that is the middle term that we wanted. So that's great. So our factoring worked, but notice that both factors are the same. So lucky us, so we only have to solve one factor because they're both the same. So 3y plus 5 equals 0. That means 3y equals negative 5, and that means that y equals negative 5/3. The other factor would give us the same solution, so when we write our solution set in the curly braces, we only have to put it down one time. So our solution set here is -5/3. So again, when a quadratic equation has two solutions that are the same, write that solution only once in the solution set. All right, now for our second objective. We've done several quadratic equations together, but also notice that you're not limited to only two factors when you use the zero factor property. You can apply this to any factored equation, no matter how many factors there are. So let's take this example here where we have 6z cubed minus 6z. So first of all, notice that this is not a trinomial, but it does have a GCF of 6z. So if we undistribute 6z, in other words, pull 6z out as a GCF, then 6z times z squared would make that first term, and 6z times -1 would make that second term. And of course, the right side is equal 0, so do not lose your equal 0. It's important that you keep an equation here. Okay, now we have 6z times z squared minus 1. Well, of course, this is a difference of squares. So this difference of squares is going to factor into z minus 1 times z plus 1. And now we have all this factoring, and it's all equal to 0. So if this times this equals 0, one of these factors has to be 0. Now, remember when we did the other example and we had the GCF out here, we were able to ignore it? That was because it did not contain a variable. But this GCF does contain a variable, and therefore this GCF is going to contribute a solution to our solution set. So if 6z equals 0, we're going to get a solution from that, and we're going to get a solution from z minus 1 equals 0 and z plus 1 equals 0. Now, if 6z equals 0 and you divide both sides by 6, then you find out that z would also have to equal 0. And so notice that you could use the zero factor property on this. If 6 times some unknown number is 0, that unknown number must be 0. All right, and for the second factor, z minus 1 equals 0, we'll add 1 to both sides and z equals 1. For the third factor, subtract 1 from both sides and z equals -1. So this time, because this was a third power equation, we got 3 solutions. So our solution set is 0 and 1 and -1 in no particular order. Here's another one. This one also starts with a y to the third. And so, of course, it's going to end up with 3 potentially different solutions. And let's go ahead and see what we can do to this. It is a trinomial, and it does have a GCF. This time the GCF is y. So if we factor out a GCF of y, then we're undistributing the y. Then what's left in parentheses will be y squared minus 6y plus 8. Notice that if I redistributed the y, it would go back to looking like this. Okay, now this is a trinomial that can be factored into 2 binomials. So I won't lose the y, but I will factor this trinomial into 2 binomials, and I will make sure that I keep all of that factoring equal to 0. Do not lose your equal sign. All right, now reversing the FOIL process here. Y squared is going to be y times y. The last term is a positive, so that tells me these 2 signs have to be the same, and they're going to have to be the same as the middle term. Okay, last times last is 8. That's got to be 2 times 4, because that way outer plus inner will add up to -6y for the middle term. Okay, now if this times this times this is 0, then one of these factors has to be 0. Either the first factor equals 0, or the second one, or the third one. If the first factor equals 0, then just 0 is one of our solutions, so that's fine. If the middle factor equals 0, then you add 4 to both sides and you find out y equals 4. If the third factor equals 0, add 2 to both sides and y equals 2. So our solution set is 0 and 4 and 2. And one last example together. Here we have a binomial times a trinomial equals 0. Well, this binomial cannot be broken down anymore, but this trinomial can be broken down into two binomials. So let's figure out what they are. X squared has got to be x times x. The last term made positive 20, so that tells us that these signs have to be the same, and they both have to be the same as the middle term, so they both have to be minus. And then I know you're already thinking that 20 is going to be 5 times 4, and that way we get the middle term that we wanted. Outer plus inner would be negative 5x minus 4x, which is negative 9x. All right, so we have this factor times this equals 0. That means one of these factors has to be 0. So we have to find out what is the x value that causes each one to be 0. So if 2x minus 1 equals 0, then add 1 to both sides, 2x equals 1. Then divide both sides by 2, and x equals 1/2. If x minus 4 equals 0, then x equals 4. If x minus 5 equals 0, then add 5 to both sides, and x equals 5. So our solution set here is 1/2 and 4 and 5. All right, I hope you're feeling a little more confident with your factoring, and I hope that you've been practicing and that it's paying off. If you will practice and think about what you're doing, you will find that you get better and better at it, just like somebody who puts together lots of jigsaw puzzles gets really good at putting together jigsaw puzzles. You just develop a feel for it, but you have to practice and be patient with yourself, and it always helps to have a way to apply that, which we've got here in this section where we've been using our factoring to solve these equations. So I hope that's been helpful for you, and I'll see you in the next section.